Hi, everybody. Welcome back, and I apologize for the lateness of this lecture, but congratulations on completing the midterm and the fact that you are now just about halfway through the class. And our first post-midterm topic will be one that we've danced around a fair bit, but not really hit head-on just yet. And it's one that you might have been wondering when that was coming if you hadn't checked the syllabus, and that is glaciers. We'll be talking about glaciers and ice this week. So by this point in the class, you should have you definitely have some geography and climatology under your belt, and you now hopefully have a decent idea of just why Antarctica is so icy. So this lecture and lecture 12 will delve into different aspects of glaciers. This first lecture will introduce the water cycle, define glaciers, and introduce several categories of glaciers based on physical form in the first half. And in the second half, I'll switch to a bit of a focus on what happens when glaciers meet the sea, as well as the difference between sea ice and ice shelves, which it turns out are actually the bit of glaciers that stick out over the ocean. Wednesday's lecture will focus more on how glaciers move and how they function as the rivers of Antarctica, and how glaciers flow in several different ways, as well as how glaciers erode the rocks underneath them. So regarding the midterm, please continue to avoid talking about it for now. By the way, I am in the process of adding the extra credit. I was very pleasantly surprised just by how many people took the practice quiz. I will probably do something similar for the final, but I am in the process of adding the extra credit points. I will send out an email about when I'm finally done doing that. I'm about halfway through. Some of you may have gotten emails already. If the extra credit points bring you to a full score, in which case, congratulations, then you might have some points left over, which I can allocate to other assignments. So in a few days, I should have a sense of what the average was with the extra credit added. I will say that the final exam is going to have some of the material covered on the midterm. The final exam is technically cumulative. However, only about 1 in 5 questions at most will relate to pre-midterm material. And on the final exam study guide, I will include a list of pre-midterm keywords that could show up on the final. And that is going to be much, much shorter than the list that you were studying for the midterm. So I'll have kind of a condensed review guide, and also one of the review sessions near the end of the course will be about the pre-midterm material to refresh you on that. The fossils lab is due this Friday on May 7th at 11:59 p.m. If you haven't already, I recommend checking out the presentation that TAs have made. It is also very worth reviewing lectures 6 and 7A. Also, there is no required article reading this week, but I recommend, you need to watch the assigned clip of Encounters at the End of the World at some point. There's a chance that there could be a quiz question on that when we have the second lecture quiz and when there are some short answer questions. There are also a few events happening. I'm recording this Tuesday night, and this already happened, but there will be some more happening that I will send an email out about. Quite a few events this week, and I hope some of you got to go to this because I'm actually really interested in this, and I didn't have time to go myself. I wanted to mention regarding the lab that some good lectures to reference. Lecture 5A about continental drift has some relevant information, as does lecture 6A, which is all about paleontology and fossils. And then lectures 6B and 7A are the history of Antarctica lectures. And it might be worth at least skimming those over again, because the lab talks about how plants have changed in Antarctica, and how that is related to climate change, how we see Antarctica's plant life look less and less like jungle life and more like temperate forest, like North American forest woods, and then no forests at all after the opening of the Antarctic circumpolar current. Some things to think about are the concept of continental drift and how fossils have helped prove that, how some fossils are body fossils of the organism itself, and some are trace fossils that are evidence of something the organism has left behind. Maybe it's a coincidence, I suppose, that I'm wearing this shirt, but it helps me get in the mood for geology. So this lab is all about fossils, and it is one that I'm a little bit sad that we have to do online because handling the fossils is really fun. But you also want to know Pangaea. Antarctica was part of Gondwana, part of all the southern continents, and Gondwana was at one point part of Pangaea. And then you want to think about how fossils indicate depositional environment, how the presence of a particular type of fossil can tell you whether the rock it's found in formed on land or in the ocean. Clam fossils would indicate a marine depositional environment. petrified wood would indicate a forest. I also wanted to mention that reading assignment number 2 is now open, and this is formatted very similarly to last time, except that this time the article you're looking at is a peer-reviewed scientific journal article. This is one that is detailing research written by the scientists themselves, or possibly the historians or social scientists if you're a bit more interested in that. And for science articles, I recommend, if you want to do a targeted search, you can access the database GeoRef through the UCSB Library Online system. If you are logged in with your UCSB credentials, you have access to a good number of articles. So make sure that you're logged in. And that's one nice thing about using the databases. If you're logged in with your UCSB password, then you can actually get a lot of the PDFs much more easily. If you have trouble finding something that looks interesting, I will see what I can do to help. Also, feel free to contact me for suggestions or to bounce ideas off me. I've given you some examples of articles that you can use as some of the articles that I've assigned. They do not need to be as long or as dense as those necessarily. The Antarctic Circumpolar article was a bit dense, I will admit. And the article you picked does not have to be quite that intense, but I gave that as an example of the overall intent of the articles that I'm trying to have you work on. The intent being, this is primary research. This is the scientists actually doing the research. So this time you'll need to address what the research goals of the authors are. And on that note, I would really recommend against picking an article that is a summary of other people's research, because it'll be very, very hard to do the assignment properly that way. You also need to address what the author's results are and whether those results are what the authors expected. And please make sure to include a link. The TAs are in the process of grading assignment number 1, by the way, so you should all have grades for that quite soon. And again, you could hypothetically pick an article that is about penguin feces. Richard gets full credit for sending this one to me. So Richard, I don't know if you knew that I was going to put this in the lecture, but I was. Anyhow, this is apparently a real article, and I would indeed accept a write-up on something like this. I have not read the whole article yet, so I'm still kind of curious as to how they got the funding to study the velocity of this. But anyhow, I put a silly example for the assignment number 1, so I thought I would put a silly example for this one also. Now, moving on to today's material, in the first half of the lecture, I'll talk a little bit about the water cycle and how glaciers fit into that, introduce what a glacier is and some different physical types of glacier. And in the second half of the lecture, I'll talk a little bit about ice streams, how glaciers flow as ice streams and as ice falls, and what happens to glaciers when they reach the sea. I'll have a little bit about sea ice and how that is separate from the ice shelves that are actually the extensions of glaciers. So in any cycle, the substance of interest, whether it's water or carbon or nitrogen, that substance is shown flowing between different reservoirs. The water cycle is a diagram that shows you how water moves between different places where water resides, where water is stored in a sense. And in the case of water, that includes phase changes. Water goes from being frozen ice to liquid water to water vapor. Some other cycles, like the carbon cycle, show chemical changes that involve, say, hydrocarbons being converted to carbon dioxide, and we'll come back to that when we do climate change. With the water cycle, it chemically doesn't change. It's water no matter whether it's a solid, a liquid, or a gas, but it changes phase. And a reservoir is any place where water spends a meaningful amount of time, whether that be the oceans or freshwater lakes or rivers or clouds or glaciers. And the water transfers between the reservoirs by either water flow or by precipitation, such as when water goes from being in the atmosphere, where it's water vapor, and goes to being liquid water and falls out as rain, or solid water and falls out as snow. Evaporation is when the water leaves the ocean and turns into vapor and enters the atmosphere. Now, with precipitation, remember that precipitation can be either rainfall or snowfall, and snowfall is a bit more important in Antarctica. The water that would otherwise fall as rain is falling very sparsely as snow in Antarctica, and that is what builds the glaciers. When the glaciers get bigger, they are said to be accumulating. When the glaciers get smaller, through either melting or calving, which means when they break up into smaller pieces, or sublimating, they are said to be ablating. And both processes, accumulation and ablation, involve the transfer of water. Accumulation involves the transfer of water to glaciers, and ablation involves the transfer of water from glaciers, ultimately to the oceans. Now, very little of Earth's fresh water is actually available, and very little of Earth's water to begin with is even fresh water. It turns out that glaciers, sea ice, and ice sheets are actually where most of Earth's fresh water is. Remember that from the formation of Antarctic bottom water, sea ice does not tend to incorporate the salt in the water, so that sea ice is frozen fresh water. Now, most of the world's water is in the oceans, and it's too salty for people to drink. Fresh water is only about 2.5%, and then about 2/3 of that 2.5% is glaciers and sea ice and ice caps. Then you have most of the remaining third being taken up by groundwater. Only about 1.2% of all of the fresh water is actually at the surface in the form of rivers and lakes at any given time. And the amount of surface water available to people isn't that much. You'll notice that a big portion of this 1.2% is taken up by ground ice and permafrost. And permafrost is the frozen ice within the soil in the tundra, the portions of Alaska and Siberia close to the Arctic Circle. So you can see that there's not actually that much fresh water available. A lot of it is locked up in glaciers, and a lot of the water that is locked up in glaciers is particularly locked up in the East Antarctic ice sheet, the largest glacier in the entire world. Right now, the Earth is actually in a relatively dry point in its history because so much water is locked up in the ice caps. There would be more that was free to circulate if there were no ice caps, and that's actually an important point we'll come back to when we talk about climate records, because one way that we understand how climate changes over geologic time is we actually study how water gets locked up in the glaciers and how that affects something known as the stable isotope ratios of water. We'll return to that later, but that's something to put on your radar for now. And a visual aid to this, there is a tiny dot above the Florida Peninsula, and that is how much water is actually present in lakes and rivers. The slightly larger dot near Kentucky is all of the liquid freshwater. The largest orb above the central United States is all of the water that's in or on or above the Earth in the atmosphere. And you can see that this map is drained. You can see that it's like the oceans have been drained and that you have this mid-Atlantic ridge down here, and the oceans are kind of these basins. They are basins. They're what water normally fills. And it turns out there is not actually that much water on Earth. I think this is a cool way to visualize it because it shows you that water is, we have plenty of it, but there's not as much as you might necessarily think. Although we're in California, a lot of us are in California, so at least we have some intrinsic sense of how scarce water can be. Now, what is a glacier? A glacier is an accumulation of compacted snow. The ice in the glacier compacts under its own weight, and the glacier also moves under its own weight. And yes, glaciers move. Glaciers move extremely slowly, and we will delve some more into the specifics of how they move next lecture. They form where there is more snowfall than snow melt, and this is the case in Antarctica. There is very little precipitation. Remember that Antarctica is in a high pressure zone where a lot of the moisture has already been lost at 60 degrees south. But what precipitation does make it in the air mass that reaches the South Pole, that largely falls as snow and not rain. And because it's so cold, it accumulates and doesn't really melt. It has time to sit there without melting, and so the snow begins to pile up. And as it piles up over tens of thousands of years, it becomes compact under its own weight, and it also begins to move downhill under its own weight. And something we'll come back to is that glacier ice is not the same as snow ice. Glacier ice is very compact. Only about 20% of the space is taken up by air bubbles, whereas with snow, it's 90% air. Snow is 90% air, 10% ice. Glacial ice is 80% ice and 20% air, so it's very compact. And you find glacial ice on the bottom of a column of snow. Now, an ice sheet is the specific type of glacier found in Antarctica. It is a glacier that covers more than 50,000 square kilometers, and there's only 3 true examples of ice sheets that still exist today. Those are the Greenland ice sheet and then the 2 Antarctic ice sheets, the East and West Antarctic ice sheets. Now, during the last glacial episode of the current ice age, and that is the period in which the glaciers were at their greatest extent, the ice sheets covered much of North America as well as many of the other continents. And this map shows the coverage of glaciers during the last glacial maximum. And you can see that all of Canada and a lot of the northern US were covered in glaciers. So was Northern Europe and a lot of Siberia. You even see some glaciation spreading out from the Himalaya and also in the Andes Mountains. You don't have quite as much land in the southern hemisphere, so you don't get as much ice here, but you still have the Antarctic ice sheet. And these ice sheets that cover North America and Europe and Asia are just about gone now. You have some glaciers up in the mountains, of course, but you don't have ice just covering everything. And it's interesting to think about how places like Canada used to be a bit more like Antarctica, and that there were glaciers covering much of them. Of course, the difference is that those glaciers are gone there now, and over the thousands of years since this last glacial maximum, plants have regrown there. Antarctica is still covered in an ice sheet, and it's also too cold for plants to exist there. Now, the northern hemisphere ice sheets have shrunk back to Greenland, which is a lot smaller than the Antarctic ice sheets. The ice covering Antarctica mostly belongs to the West and East Antarctic ice sheets. If you put them together, they are more than 1.5 times the size of the continental United States. And the entire Mississippi River system would need 50,000 years to completely drain all of the meltwater if the entire mass of the 2 ice sheets were going to melt. So it's a lot of ice, and it's had a long time to build up. It has been accumulating since the Oligocene epoch, tens of millions of years ago, about 20 million years ago. The East Antarctic ice sheet is by far the larger one. It is over 4 kilometers thick at its thickest point, and it covers the East Antarctic craton, the continental mass that we've had to study using earthquake waves largely because we can't easily go under the ice to study the crust itself. You might remember me in the geography lecture mentioning that the East Antarctic ice sheet flows divergently, and we'll talk more about that later. But what this means is that the ice is accumulating near the center of the ice sheet and spreading out in all directions towards all of the surrounding seas and oceans. Now, the West Antarctic ice sheet is smaller than the East Antarctic ice sheet, and it is also smaller than the Greenland ice sheet. It has convergent flow. You have ice accumulating here close to the boundary with East Antarctica, and it flows westward and northward, combining into a single large ice stream. And an ice stream is a fast region within a glacier where ice is flowing most noticeably. And yes, glaciers flow, and some parts of glaciers flow faster than others. Now, West Antarctica is presently melting. The ice sheet is losing mass, and part of this relates to the fact that the ice sheet terminates in the peninsula, which is experiencing the most notable warming on the continent, and the ocean around the Antarctic peninsula is also getting especially warm. It is, remember, the most northerly part of Antarctica. You can see just how close it is to South America here. Greenland, the ice sheet in Greenland is just slightly bigger than that in West Antarctica. It is pretty tiny compared to Antarctica overall. You'll notice that you have this ice sheet covering Greenland. This is not an ice sheet. This is sea ice. This is not ice that accumulates on land. This is ice that forms from the freezing of ocean water. and it is seasonal. There's some pack ice that lasts through the whole summer, but its extent gets larger and gets smaller seasonally. And the idea with an ice shelf is that over a steady period of time, over decades and centuries, it is pretty stable. You don't get a lot of seasonal variation. That is, of course, changing because human activities are greatly modifying the climate. But the Greenland ice sheet is the only ice sheet outside of Antarctica, and the Arctic is warming a lot faster than the Antarctic because it is mostly ocean. The oceans are warming faster than the oceans have absorbed a lot of heat, and that is starting to affect the Arctic a lot. So Greenland is surrounded by the warming ocean and is seeing higher and higher air temperatures and thus higher melt anomalies. And that's what this diagram is showing. A melt anomaly is a higher than expected degree of melting of its ice sheet, excuse me. Now, if you've ever looked at a map of Iceland or the Canadian islands to the north of the mainland, you might have seen little splotches of ice. And those are ice caps. They are a mini ice sheet, basically. Ice sheets are one type of continental glacier. And continental glacier is a term for how glaciers are or are not affected by their surrounding topography. Continental glaciers are not constrained by the surrounding mountains or valleys. They flow over everything and they sort of sit on top. They cap everything. So you have an ice cap, you have Barnes ice cap on Baffin Island, and you have the Vatnajökull ice cap in Iceland, which I was lucky enough to see. You can see a glacier flowing out of it, and it's kind of hard to see in this picture, I'm realizing, but in the interior, you get this ice that's just sort of covering everything, a few mountains sticking out from it. It doesn't cover the entire island of Iceland, but it covers a good chunk of it. And so these are remnants of the ice sheets that once covered almost all of Iceland and that covered almost all of Baffin Island. They are melting rather quickly now as a result of global warming. Now, continental glaciers are glaciers that are not constrained by any surrounding mountains. One thing to note is that there's a number of different technical terms for glaciers that refer to how they flow, that refer to their shape. And one glacier will change shape throughout its course from wherever it is accumulating until it reaches the ocean or until it reaches its terminus, its end. Glaciers flow and glaciers change. Glaciers can become confined. Glaciers can start out being a continental glacier, but then they can flow towards the outside of the continent and start to be more constrained by valleys and mountains, which is indeed what happens in Antarctica. In general, a term for a glacier that is confined by the morphology of the surrounding mountains is an alpine glacier or a mountain glacier. And an alpine glacier carves out what is known as a U-shaped valley. Rivers cut V-shaped valleys. They cut downwards largely. Glaciers aren't moving very fast, and they also are rather broad and tend to shovel out everything in their way, as we'll talk more about in the erosion section in next week's lecture. So they make a U-shaped valley instead of a V-shaped valley. Now, alpine glaciers are relatively narrow, wide compared to a river of liquid water, but still rather narrow, especially compared to the ice sheets. Often alpine glaciers in areas like the Alps or Montana or the Andes, outside of where the ice sheets are basically, they'll start in this place called a cirque, where you have a U-shaped valley carved out by the overall presence of ice. And this bowl-shaped valley, the cirque, is where the glacier is accumulating, and it'll flow out of the cirque down into the valley. Glaciers change shape as they move down. Alpine glaciers and cirque glaciers become valley glaciers as they spread out with the valley spreading out. Downhill, the valleys will spread out and the glaciers will be spread out more as a result. And lobes of the Antarctic ice sheets actually become valley glaciers closer to the coasts. This is where they are far from the zone of accumulation where the glacier is building up. And in the Transantarctic Mountains, glaciers that are flowing from the interior of the continent suddenly become trapped by mountains and the individual lobes that are overall all coming from the central Eastern Arctic ice sheet, but they start to become more constrained by the valleys between the mountains. Of course, in some valleys, like the dry valleys, you don't have glaciers because the winds are strong enough to blow the snow away. But on the edges of Antarctica, you do have glaciers flowing into valleys and towards the oceans. Now, in the dry valleys, you sometimes have an interesting case where you do get a lobe of coming from the main glacier, and you can see that this glacier is kind of covering everything. There's some mountains sticking up, but then the glacier flows in this pass and then starts to spread out as it enters this wide dry valley here. This format, when the glacier spreads out in all directions, kind of like a duckfoot webbed out, or a webbed duckfoot spread out, this is a Piedmont glacier. And there, in a number of Romance languages, PS means toe or something like that, or foot. Piedmont literally means foot of the mountain. Piedmont glaciers are glaciers that spread out as they suddenly go from flowing down a steep valley into flowing into a rather gentle and wide valley. The glacier, which has been constrained up until this point, suddenly has room to flow out, and the ice flows out in all directions. However, what this means is that more of the surface area of the ice is exposed to the air and to the sun. So melting and sublimation, aka when snow directly goes to water vapor, can occur at a much faster rate. And so Piedmont glaciers tend to be sort of the end of the line for these glaciers. That where it's spreading out, that's also where it's going to melt more, and it's not going to really flow past the point where it becomes a Piedmont glacier. Another way to think about this is that it's a fan. It's the glacier spreading out in a fan shape, sort of like how in deserts you get this alluvial fan of sediment from flash floods, or how you get a delta fan where the river is slowing down and spreading its sediment into the ocean, dropping its ocean in kind of a fan-shaped feature in all directions. Now, the Piedmont Glacier is a particular format that you see a fair bit in Antarctica, and I think they're rather picturesque. We'll talk more about what happens to some glaciers that do actually make it all the way to the sea and don't spread out as Piedmont glaciers in the second half of this lecture. So enjoy that. And again, I apologize for the lateness of this lecture. I will be caught up tomorrow.